This is the Satellite Foundation course for GOES-R training on 3 surface-related baseline products that will be available in AWIPS. Fire products, developed by Chris Schmidt at SIMS. Land surface temperature products, developed by Yanyo Yu at NOAA. And snow coverage products, developed in part by Jeff Key at NOAA. I'm Scott Lindstrom, and I will be guiding you through this training. This training covers the products boxed in yellow on this slide. They are baseline products that should be available when GOES-R data starts to flow about 3 months after launch. At the end of this training, you will know the temporal cadence of the product generation and how the products, fire detection, land surface temperature, and fractional snow cover, are created from GOES-R ABI data. The fire products that are available in AWIPS are fire area, fire power, and fire temperature. These are created every 5 minutes for the CONUS domain and every 15 minutes for the full disk domain. That means they're created for every full disk and CONUS image available. What is now known as FDCA, Fire Detection and Characterization Algorithm, one of the topics of this training, is very similar to the WF-ABA algorithm you may be familiar with. They both deal in hotspot detection. GOES-R ABI provides improved resolution and detection of fires compared to GOES 13 through 15. GOES-R ABI has a much higher saturation temperature, for example, meaning hotter fires can be more accurately described. The improved spatial resolution means smaller fires can be detected, and more frequent scanning also aids in fire detection. Fires are always smaller than the size of a pixel. Fire detection uses the shortwave and longwave infrared bands and exploits subpixel effects. You will hear more about subpixel effects in a bit. Hot fire temperatures emit more 3.9 micron radiation than 11 micron radiation, and this enhanced 3.9 micron radiation is key to fire detection. There are other variables that are needed in the computation to clarify the differences between the infrared bands. The shortwave infrared channel has a much larger response to the development of fire within a pixel than does the longwave infrared channel. Surface temperature warming in a pixel, because of a developing fire, shifts the Planck function peak to shorter wavelengths a lot more rapidly for 3.9 microns, band 7, than for 10.3 or 11.2 microns, bands 13 and 14 on ABI. The response in the pixel differs for each fire, and those differences help in the estimate of fire attributes. Again, fires are small compared to a satellite pixel, even with 2-kilometer pixel sizes, and fires contribute more energy in shorter wavelengths than in longer wavelengths. So when a fire develops, the changes are more obvious in the short wavelength 3.9 micron channel than in the longer wavelength 11 micron channel. Compare the two channels here. The red 3.9 micron channel pixel values and the blue 11 micron channel pixel values. Value differences help establish that a fire has likely initiated at points A through G. Similarly, the larger values in the surface plot help identify where fires are occurring in the transition zone between forest and savanna in Brazil. What is the subpixel effect? Optically thin clouds, such as cirrus, do not opaquely cover a pixel. Warm parts of that pixel, the surface and any lower clouds, are more readily detected than cold parts of the pixel by shorter wavelength detectors. Conversely, cold parts of the pixel, high clouds for example, are more readily detected than warm parts of the pixel by longer wavelengths. Thin cirrus in this scene is warmer at 10.3 microns than at 12.1 microns. Compare the extent of the purple in the rainbow enhancements, because the shorter wavelengths are more sensitive to the warmer temperatures, and the longer wavelengths are more sensitive to colder temperatures. Similarly, 3.9 microns is more sensitive to warmer temperatures than 10.3 or 11.2 microns. When the Fort McMurray, Alberta fire started in early May of 2016, it was first detectable in the GOES 13 3.9 micron channel of 1845 UTC, before it was apparent in the visible or the 10.7 micron channel. That warmth is at 3.9 microns because the peak amount of emitted radiation has a wavelength of about 2800 divided by the temperature. This is called Wien's law. If the temperature is about 800 Kelvin, then that means a lot of 3.9 micron radiation will be emitted, and it will be detected by the satellite. Fires develop and move very quickly. GOES 13 and GOES 15 standard scanning was every 15 minutes, and things could change much more quickly than that. ABI will scan CONUS every 5 minutes, producing fire products with that cadence. 1-minute data will be available in 2 separate mesodomains that can be placed over a fire to monitor closely the fire's evolution. Fires also change power at very small time scales. This plot compares 1-minute data from GOES 14 and an SR-SOR operations, that's super rapid scanning operations for GOES-R. Those are the white points, compared to standard scanning from GOES 15, which are the green points. The red shows the line of average pixels for GOES 14. The yellow shows the line of average pixels for GOES 15. Look how quickly values change in the red line, the 1-minute data, compared to the yellow line, the much smoother 15-minute data. This is a good argument for wanting good temporal sampling when monitoring fires. Polar orbiting satellites such as MODIS also can detect fires. This is an image of a fiery scene over Sumatra. The red polygons show automated MODIS fire detection, and they line up nicely with the observed smoke plumes. The GOES-R FDCA algorithm applied to Himawari 8 data detected fires for the same time. The MODIS polygons are still on this image, and so are Himawari 8 detections. Processed fire means it's been characterized fully, that is, area, power, and temperature are computed. Magenta is a cloud-covered fire, and the FDCA algorithm from Himawari 8 data is doing a better job of detecting fires underneath the smoke plumes than the MODIS data. Let's switch topics now to land surface characteristics and fractional snow cover, 2 additional GOES-R baseline products. Land surface temperature is computed hourly in all 3 domains, full disk, CONUS, and meso. CONUS and meso domain resolution is 2 km. The full disk domain has a resolution of 10 km, that is an aggregation of a 5x5 array of 2 km pixels. Snow cover, which is fractional snow cover, is computed hourly for full disk, CONUS, and mesoscale domains at 2 km resolution. Land surface temperature is computed from 2 ABI bands. You generally cannot use a single infrared channel for this because water vapor absorption in most channels on ABI means that detected temperature is cooler than the actual ground, because energy emitted from the surface is absorbed, partially, by water vapor and re-emitted from a higher and therefore colder part of the atmosphere. At shorter wavelengths, around 3.9 microns, you face the additional challenge of reflected solar energy. The split window difference uses data from 11.2 and 12.3 microns, that is, bands 14 and 15 on ABI. The amount of water vapor in the atmosphere is related to the split window difference, so a water vapor correction can be computed for either detected brightness temperature. Land surface temperature is computed hourly for the full disk, CONUS, and meso domains, and values range from 213 to 330 Kelvin, that is from -60 Celsius to 57 Celsius. The differences in brightness temperature for the split window difference does consider the different dependencies on zenith angle for the 2 channels. This figure shows cooling in each GOES-R ABI infrared band that is a function of a local zenith angle only. In general, as the local zenith angle increases, that is, as you get farther and farther from nadir, brightness temperatures will be cooler because more of the radiation detected from the satellite is emitted from the cooler upper atmosphere. In particular, for land surface temperature, band 15, 12.3 microns, shows greater cooling for larger zenith angle than band 14 at 11.2 microns. Here is the MODIS-derived land surface temperature over the high plains. This is Colorado, western Kansas, and parts of Nebraska. Cumulus clouds show up as missing data. River valleys are typically cooler, and mountain ridges are apparent. Usually, the land surface temperature is warmer than co-located METAR values that are recorded about 6 feet above the surface. Satellite-derived land surface temperatures will neatly articulate the marine boundary layer, or a sea breeze, to give excellent mesoscale observations of small-scale temperature gradients. The Colorado River also stands out nicely here as a cold sliver. Are you expecting freezing temperatures? Land surface temperature fields can tell you exactly where the temperature is most likely to be sub-freezing. You might want to make an enhancement for such an event that highlights the region around plus or minus 5 Celsius. Fractional snow cover is also a day 1 baseline product for GOES-R. This is a daytime-only, reflectance-driven product. There is a snow, no snow product, but also a fractional pixel snow cover product. This is produced every 60 minutes for all domains, full disk, CONUS, and meso, at 2 km resolution. GOES visible imagery from March 1, 2009 shows a snowband over the Central Plains and also an east-west oriented snowline over central Wisconsin. The ABI snow fraction computed with MODIS data is shown on the inset. There's good agreement.